Aircraft are fitted with flaps to reduce the takeoff and landing run. The reduction in takeoff and landing run is achieved by reducing the minimum operating speed. The minimum operating speed typically provides a 30% margin of safety above stall speed. Here you can see the transpose lift formula you were introduced to in previous lessons. Please note the typical stall speed for a jet transport aircraft of 131 knots, indicated airspeed, and the associated minimum operating speed that is 30% higher. You can see that increasing the maximum lift coefficient, CLmax, gives a decrease in stall speed, and therefore a decrease in minimum operating speed. CLmax is increased by temporarily increasing the camber of the wing with flaps. Only trailing edge flaps are illustrated for the moment. Flaps are a hinged portion of the trailing or leading edge of the wing that can be deflected downwards and so produce an increase in camber. For low-speed aircraft, the flaps will be on the trailing edge only, but on high-speed jet transport aircraft, there will be flaps on the trailing edge and the leading edge. We will consider the common types of trailing edge flap first. The plane flap is usually fitted to light aircraft and is of simple construction. The plane flap gives a good increase in CLmax, but with fairly high drag. Here we show a 10-degree flap selection. 10 degrees of flap will be ideal for takeoff, because CLmax will be increased a moderate amount, but drag will increase only slightly. Prior to landing, flaps should be selected in small increments, and 10 degrees will be the initial selection. It should be noted that any amount of flap will increase drag. The significance of this fact will be explained later. Further flap selection will continue to increase CLmax. Selecting flap angles of 20, 30 or 40 degrees will continue to increase CLmax, but also give a significant increase in drag. So the larger angles are usually used for the approach to landing, when the extra drag is an advantage. The next type of trailing edge flap we'll consider is the split flap. The difference from the plane flap is that the split flap only moves the lower surface of the trailing edge. The next type of trailing edge flap we'll consider is the slotted flap. When the slotted flap is lowered, a slot is opened between the leading edge of the flap and the trailing edge of the wing. The slot directs high-energy airflow from the bottom surface of the wing onto the upper surface of the flap. This increases the kinetic energy in the boundary layer over the flap. Therefore, the slotted flap can be lowered to a larger angle before airflow separation begins. This allows a greater increase in CLmax with much less drag than is possible with either the plane or the split flap. A slotted flap can have more than one slot. Double or triple slotted flaps are usually fitted to larger aircraft, which can offset the higher weight and greater complexity against the increased efficiency. The most efficient type of trailing edge flap is the Fowler flap. Fowler flaps are fitted to both large and small jet transport aircraft. When flaps 1 is selected, the first movement is rearward, which increases the wing area. You can see that increasing the wing area also decreases the stall speed and the minimum operating speed. Flaps 1 is useful for loitering in the terminal area because there is a useful reduction in stall speed but no significant increase in drag. When selections greater than flaps 1 are made, the camber starts to increase. Flaps 5 or flaps 15 are typical selections for takeoff. As before, the larger flap settings are used for the approach to landing. We will now select flaps up. This is a non-practical selection and speed of operation. If you selected flaps all the way up like this when flying, the aircraft would sing like a stone. We are resetting the scene to consider slotted Fowler flaps. For maximum efficiency, Fowler flaps can have as many as 3 slots. This example shows triple slotted Fowler flaps as fitted to large jet transport aircraft, such as the Boeing 747. Again, this animation is not practical. We are merely showing the type of flap. You can see here the effect of the type of flap on CL max. The plain flap and the split flap have nearly the same ability to increase CL max. The slotted flap benefits from the greater angle to which it can be deployed without suffering airflow separation. But the best type of flap for increasing CL max is the Fowler flap. We now need to highlight the difference between the change in lift coefficient and the change in drag coefficient with increasing flap angle. In this example, we have selected flaps 5. You can see that the increase in lift coefficient is much greater than the increase in drag coefficient. With a selection from flaps 5 to flaps 10, you can see the increase in lift coefficient is less, while the increase in drag coefficient is greater. As the flap angle is increased, there will be a progressively smaller increase in lift coefficient and a larger increase in drag coefficient. This is the reason why the larger selections of flap are reserved for the landing approach, when a large amount of drag is a benefit. For takeoff, only the smaller flap angles are used, because drag must be kept to a minimum to optimize aircraft acceleration. This will be discussed in more detail in later lessons. The CL angle of attack graph shows a reduced stall angle with trailing edge flaps selected. This is because the lift curve is plotted using the original chord line, before the flaps are lowered. When the pilot lowers the trailing edge flaps, the wing camber is increased, and if the pilot did not prevent it, lift would increase. As the flaps deploy, the pilot must reduce the angle of attack so that the effective angle of attack remains constant and that lift still equals weight. Please remember that any amount of flap will increase drag. We have already seen that CL max increases as the flaps are lowered, but unfortunately drag will also increase, so we need to consider LD max. We must generate enough lift to balance the weight, but at the same time, drag must be a minimum. Therefore, drag will divide into lift the maximum number of times. We call that LD max. The following illustrations will show the efficiency of flaps. The greater the LD max, the greater the aerodynamic efficiency. If a tangent is drawn from the origin of the graph to the curve of the lift drag polar plot, the angle between the straight line and the horizontal axis is a measure of LD max. We will now compare the aerodynamic efficiency of the previously mentioned types of flap with that of no flap. Here you can see the CL-CD polar of the plane flap. Notice that the angle between the straight line from the origin and the horizontal axis is less than that for no flap. This shows a decrease in LD max, which is a reduction in aerodynamic efficiency. This is the CL-CD polar of the split flap, together with the plane flap. Notice the angle between the split flap straight line from the origin and the horizontal axis is again less than that for no flap, but pretty much the same as the plane flap. Therefore, the plane and the split flap have approximately the same aerodynamic efficiency. Now you can see the slotted flap polar. Less drag is generated, and it is more aerodynamically efficient than either the plane or the split flap. But again, LD max is less than with no flap. Here, we see the most aerodynamically efficient type of trailing edge flap, the Fowler flap. But once again, it has a lower LD max than no flap. Does an understanding of reduced LD max with flaps down have a practical application? Yes. It is a very important takeoff climb consideration. We have learned that the use of about 15 degrees of flap reduces the takeoff run. That's why flaps are fitted. But any amount of flap reduces the ability to climb. We can see that takeoff flap reduces the takeoff run required, but also reduces the ability of the aircraft to climb. When carrying out aircraft performance calculations prior to flight, this conflict must always be considered. Depending on the length of runway available and any obstacles present during the initial climb, it might be better to use no flaps for takeoff. This will be explained in more detail in future lessons. Flap movement, both up and down, may generate an aircraft pitching moment. Any pitching moment generated is due to movement of the centre of pressure, CP, and changes in downwash. Note that the CP is aft of the aircraft, CG. This generates a nose-down pitching moment. The aircraft, however, is in equilibrium because of the matching nose-up pitching moment from the downforce on the tail. First, we will consider movement of the CP. Only the top surface pressure distribution will be shown. As the flaps deploy, there is a general increase of suction on the top surface, but there is also an increased acceleration of the airflow in the vicinity of the flap hinge. This produces a localized reduction in pressure, which moves the CP aft, and an aircraft nose-down pitching moment is generated. Let us now take a look at the effect of downwash. You can see that as the flaps deploy, the downwash increases. This increases the downforce on the tail and generates an aircraft nose-up pitching moment. It is now obvious that flap deployment generates two pitching moments, a nose-down pitching moment from the wing and a nose-up pitching moment from the tail. So, if you are asked the question, what pitching moment does the aircraft experience when trailing edge flaps are deployed? The only answer you can give is, it depends. The net pitching moment the aircraft experiences will depend upon which of the two pitching moments is dominant. On some aircraft, the net pitching moment will be nose down. On some aircraft, the net pitching moment will be nose up. And on other aircraft, there will be no net pitching moment. However, if the aircraft you are flying has fouler flaps, it will usually generate a net nose-down pitching moment when the flaps are deployed. Because fouler flaps increase the wing area by moving rearwards when deploying, a larger nose-down pitching moment is generated. This gives an increased tendency to generate a net aircraft nose-down pitching moment when the flaps are lowered. If a T-tail is fitted to an aircraft, it will also influence the net aircraft pitching moment. A T-tail is attached in a higher position, so the change in downwash from flap deployment will have a smaller influence on the tail force, and a reduced nose-up pitching moment is generated. This animation repeats the fact that as flaps are lowered, the pilot must decrease the angle of attack, so that lift remains the same as the weight. Therefore, with flaps down, the aircraft will fly in a more nose-down attitude. On approach to landing, this is an advantage, as it gives a better view of the runway. Because of the high minimum speed of jet transport aircraft, even the fitment of trailing edge flaps does not reduce the takeoff and landing run to acceptable values. For this reason, in addition to the most efficient trailing edge flaps, jet transport aircraft must also be fitted with leading edge flaps. The next lesson will examine leading edge flaps in detail, plus the operational details of high lift devices.